Hello, everyone, and welcome to the NAGT webinar series. This webinar series is your one-stop shop for strengthening work in Earth education. Webinars in the series feature novel and innovative work in Earth education, research and pedagogy, new teaching materials, and the classroom and professional experiences of people like you. That NAGT webinar series is free and open to the public, and we encourage you to invite your colleagues to attend and join the discussion. Before we get started, please take a moment to review the Zoom controls on the screen. We are probably all very familiar with them at this point, but just a reminder to keep your microphone muted and your camera off so that we can avoid background noise and other things for this recording that will go up on the website. On the screen is a link to the webinar series where you can find the full webinar schedule, an archive of past events, and information on our sponsoring projects and programs. You can find slides, resources, and recordings of each webinar, including today's, through the webinar archives, and I will post those links in the chat as well. A reminder that participants in all NAGT meetings and events are expected to abide by the NAGT Code of Conduct, which applies in all venues, events, and online forums associated with NAGT. So please read that NAGT Code of Conduct and be sure to follow those things. Today's webinar is titled Studying Atmospheric Processes with Airborne Data, and our presenters are Armin Sarushian and Joe Schlosser, and I will turn it over to them for the remainder of the webinar.
Okay, thanks, John, for you and the rest of NAGT for having us give this presentation today. It's really a pleasure for us. So Joe will handle the controls throughout the session, and this is really meant to be an interactive session to try to teach you all about how to access and use and visualize our data and what kind of science we can do with it. So on the screen here, you could see pictures of two NASA Langley Research Center aircraft, which were used for all of the flights as part of a NASA mission that we're part of called Activate. And we are representing the Activate team. So I'm from the University of Arizona. Joe was a former PhD graduate of mine who's now a postdoctoral fellow at NASA Langley himself. And so all those institutions on the bottom right of the slide represent various team members as part of the Activate science team. But a big part of today is we're trying to grow our team of people who will use our data, including hopefully some of you. So with that, we will proceed to the next slide, which is just an outline of the session today. I know we have an hour, so we want to do some interactive things that Joe has designed. But before that, I'm going to go over the background of the topic that Activate is studying, so the topic driving all the data that was collected. And throughout the session, I will be chatting, hopefully, with anybody who has questions. I know some of the activities, even though we've tried to do it slowly, might be too fast for you. Please rely on the chat so that you could at least learn more about how you can use the data if the activities are going too fast for you. So with that, let's roll forward, Joe. So in terms of learning objectives, we have two. Okay, so I will go over objective one in my first few minutes here, which is motivating research into what we call aerosol cloud interactions and the importance of airborne measurements in addressing those interactions. And then Joe's going to be using the Google Collaboratory environment to do all the activities with accessing and visualizing the data. Okay, so let's move on. So in terms of background, so aerosol particles is really what drives a lot of the science we're interested in. So these are particles, you will be very familiar with them because the reason we've been wearing masks for so long is that the COVID disease, you know, it's exchanged by respirable aerosol particles. Other examples of particles are dust and smoke, and these range widely in size, particles from as small as a nanometer to hundreds of micrometer. So several orders of magnitude, these particles span in size. Not only is their size really complex, but their composition is very complex. So the combination of all those complexities makes it very hard to understand these particles. And you got to know something about their size and chemistry to know how they'll interact with sunlight and water vapor in the atmosphere, which is important for all kinds of things like visibility and climate. In terms of all environmental causes, particles kill more people globally than anything else, including bad water. And that's interestingly enough, driven mostly by bad indoor air quality, not so much outdoor air quality. And in contrast to greenhouse gases like CO2, this might be interesting for some of you, particles actually have a net cooling effect. So when you think of pollution, not only do we have these gases coming out like CO2, but we could have aerosol particles, and particles are bigger than gases. So what they can do is reflect sunlight back up to space when it's first trying to come down. So this leads to a cooling. Okay, so this little schematic on the bottom left of our slide shows you how you can have particles that are directly emitted from different sources on the right, like volcanoes. You could have soil erosion. Plants emit particles directly. These are called primary aerosol particles, and they tend to be big. But we also have what are called secondary aerosol particles, which originate from gases that are emitted, which then undergo reactions in the atmosphere to form products that could then condense onto existing particles or even make new particles themselves. So these particles can come from human-made sources and natural sources. And on the right are just pictures of, major types of particles, like sea salt is a huge source of particle, is a major type of particle globally because of oceans covering 71% of the global surface area. So when waves break, you get a lot of sea salt ejected in the air. And when we see a dust plume coming off of Northern Africa, you can see biomass burning coming off of southern parts of Africa. And then there's a volcanic eruption from Iceland, as you can see, spewing out dust and ash in the air. So Joe, let's go to the next slide. Now, not only do particles directly reflect light to cool the planet, but the only way you can make clouds and cloud droplets is you need a seed, and those are these particles. And clouds are very reflective because they're white, as you can see here. So particles indirectly can cool the planet due to their role in cloud formation. Turns out clouds are very complicated and we cannot fully understand them. And this is linked, these interactions between particles and clouds are linked to the largest uncertainty in our understanding of future climate change. So the best visual illustration that we could probably provide to tell you about these interactions between particles and clouds is shown here. You see a cloud deck over the ocean, but there's these thin, bright white lines, which are called ship tracks. So over the ocean, it's pretty clean, but when you have a ship moving by, one of these big cargo ships, they emit lots of particles in a very narrow line, and these particles go into the clouds and they can make lots of very small droplets, which adds surface area to reflect more light back up to space. So depending on the weather and the meteorology and the types of particles you have and the number of particles you have, you can maybe have brighter clouds and clouds that maybe rain less and can live longer. So let's move on to the next slide. So I know this is a busy slide, but there's a few key punchlines here on the left and some quotes. The Intergovernmental Panel on Climate Change has an assessment report that comes out every few years. They kind of assess the state of the science, state of our knowledge of how humans are perturbing the planet's energy balance. And they consistently in each assessment report year after year are saying that clouds and aerosols contribute to the largest uncertainty in our estimates of the planet's energy budget. And it's those interactions between particles and clouds that are the most uncertain, which is what we are trying to study as part of the Activate mission with our airborne flights. And so on the bottom left is another key report, the NASA Decadal Study Report, saying how to really study these interactions, we need to put together all of our tools, not just airplanes, but we have to use models, satellites, really anything, because it's such a complex system. Clouds, you can't access them and put them in a lab to study them easily. You really have to get up into these clouds, and that is best done with airplanes. So let's move forward, Joe. And this is kind of a schematic to show you or to have you appreciate the complexity of the aerosol cloud meteorology system. So ACTIVATE it stands for Aerosol Cloud Meteorology Interactions over the Atlantic Experiment. It's a mouthful, it's a forced acronym, but ACTIVATE is the process by which a particle becomes a droplet. And that's represented here on the schematic. But there's a whole lot of other things going on here too, with all these arrows, all these processes. And it's really hard to disentangle all these different processes when you're collecting data, especially from satellites. So what we try to do is collect lots and lots of statistics with airborne platforms to try to get at each of these different processes to better understand them. The challenge is how to disentangle the effects of particles from meteorology on the actual clouds. So that's been sort of a really big challenge that we're trying to address with gathering lots and lots of statistics with sophisticated measurements. So Joe, let's move to the next slide. So historically, the way we go study these interactions is with you could use a single plane, and it does this type of flight pattern in the animation where the plane can fly below the cloud, in the cloud at different levels, and then above the cloud. To really study the cloud, you got to study the whole column, including what's below, in, and above the cloud. All of it matters. But with a single airplane, you have limitations. You can't necessarily fit all the instruments you want on a single plane. This entire procedure can last about an hour. So by the time you're at the top of the cloud, that might not be directly representative of what was going on below the cloud anymore, because it's a transient system. And typically these field campaigns don't last long. You go somewhere for a month or two, so you can't do a lot of flights necessarily, and you don't get a lot of seasonal factors because you only fly in 1 or 2 months, so you can't study the range of clouds that could exist in a region. So what we're doing in ACTIVATE, as we'll show on the next slide, Joe, is we designed an experiment where you use 2 planes, as shown here, that can fly in vertical coordination with each other. The King Air at the top flies above the Falcon, and so they're really in the same vertical column. So we're gathering data below, in, and above the cloud at once. So this is a bit of an advancement upon using just a single plane. The King Air looks down with remote sensors, a LiDAR and a polarimeter, and Joe's going to talk about those in his activities. And it also launches what are called drop zones, which can give you a vertical profile of weather parameters. The Falcon that flies low is getting direct measurements, which are called in situ measurements of gases, particles, cloud properties, and all that. So it's really flying in those boundary layer clouds that we're most interested in. So we go do these flights over and over and over in a disciplined manner over the Northwest Atlantic Ocean, which is an excellent region for our work. And we're flying in different seasons, and we float over 3 years. And our last flights just concluded at the end of June. We did about 162 joint flights. So all the data are in the process of being archived for public use. So let's go to the next slide. This is just a picture of the 2 planes. If you're interested, our typical flights are about 3.5 to 4 hours. The air speeds are fairly similar. We keep these coordinated at all times. In the next slides, I'll show you really quickly the instruments on the planes. And I don't have nearly enough time to get into the details, but we can talk about it later in the chat. So the bottom plane has all these different instruments to do the direct measurements of aerosol, cloud, and weather parameters. And it's also studying trace gases like ozone, CO, CO2, and water vapor. So it's a very small plane, but we cram a lot in there. It's very, very tight in there. The next slide is going to show the King Air. So we have the HSRL2 LiDAR, a polarimeter, and a drop zone launcher. So that's kind of what the planes look like. And this is really my last slide, and Joe's about to start our activities, but I want to just mention a summary of all of our instruments are already posted, pre-recorded slides, if anyone's interested, at this link on the right. And we'll post all of the slides in this recording online too, in case the activities we're about to do go too fast for you, because you needed to have an Earth data account in advance, and I'm not sure everyone has that. So if things move too fast, again, let's rely on the chat, and I'm happy to talk to people about anything as Joe does the activities. So with that, I'll hand it over to you, Joe.
Oh, yeah. Okay. So thanks again for your time today. The first thing I'm going to go ahead and show is just an example of the flights that Armin was describing. So this video will be posted along with the slides, but it just shows us a synchronized video of the forward camera with the flight track being plotted, of the altitude of the aircraft being plotted along with time. Obviously, all the flights start with a takeoff and end with a landing. And then after that, it's going to transit to a location where it can actually start sampling, and at which point it'll start the cycles that Armin was describing, wherein the aircraft will fly in the boundary layer near the surface, and then it'll sample just above the boundary layer, and it'll repeat this kind of sampling throughout this entire flight. This one in particular is focused on clear air measurements, so very much just looking at aerosol particles themselves and not as much about the cloud interactions. However, many flights did also include a hefty amount of cloud sampling that went along with the aerosol sampling and kind of changed the flight pattern slightly just to make sure that the clouds were being sampled accordingly. So as you can see here is the Falcon aircraft is descending down to the surface, starting out with the near surface sampling, and then which marks the beginning of the ensemble. The blue lines are actually just the dropsondes that were being let out by the King Air, just to show you that how they are sampling through the atmosphere. And those some of the information contained in those dropsondes can be compared to that within the measured by the Falcon as well. So just to remind everyone, min-out is the minimum altitude, ABL is above the boundary layer, BBL is below the boundary layer. The RS stands for remote sensing, and then it does this kind of pattern twice and continues on through the flight. So I'm not going to go through that whole thing, but if you do want to watch it, we're going to go ahead and post that video as well. So I'm going to minimize that. And the first activity we're going to do is actually just going to be getting everything set up so that we can actually download the data from the Activate Data website and then be able to perform some quick visualizations analogous to the one that I kind of just showed, but not videos. So after this activity, we're going to have a Google Drive that looks like this one, but we're going to go ahead and start this activity. So just to make sure, again, Armin was mentioning you want to have two things really started beforehand. If you're quick, you can really set these up now, but these documents will be made available to show you how to set up a Gmail account and then an Earth Data login. And this Earth Data login can be utilized for a lot of different data, not just Activate Data. However, it is necessary for Activate Data. So again, we're going to start this activity. So if you want to follow along, now's the time. And the first thing that we're going to want to do is we're going to want to go to our Google Drive by going to drive.google.com. And we're going to want to set up a folder for the Colab environment. And so we're going to hit new, we're going to hit new folder, and then we're going to name that Colab, without capital C, and then underscore notebooks with a capital N. And just make sure that yours looks exactly like that with no extra spaces and the capitalization is correct, because that will be important later on. And then you'll see this Colab Notebooks folder there, and our directory should look like that one. The next thing we're going to want to do is install the Google Colab environment, and the way we do that is by going to Get Add-ons. This is this little arrow to the right-hand part of the screen. We'll select that, and then we're going to type in Colab. And by the time you type that in, you'll see a pop-up, and it should just say Collaboratory. Make sure to click on that one. The icon should look like this, so you want to navigate over to that. And then once you click that, hit Install. Make sure you're okay with giving permission for this. And then also make sure that if you have multiple Google accounts, that you're using the correct one for that you set up for this. And then once that's done, it'll say it's installed. You'll just hit done. It's important here to make sure that you exit out and navigate back towards that. So just close that and then go back to the Google Drive again, just by again typing in drive.google.com, just so that we can make sure that Colab is installed correctly. And also to verify that, we're going to go back to the Git add-on and type in Colab again, just to make sure it says installed there. Okay, so now the next step is actually going to be putting a few files in here that we've set up for this training session, or these training sessions rather. And in order to do that, Armin's going to go ahead and put a link, this link in the chat, and you want to navigate to that link, which is a GitHub that hosts 3 files, including the Jupyter notebook that's utilized by Google Colab, a leg type CSV, which is just an index file to know what each of the leg types are, and then just a simple README. And you'll want to click on code, and then scroll down to where it says download zip, and select that. Once you've selected that, it should go to your downloads folder. And just a quick note that it's important to mention that this is for Windows 10. If you have Windows 11 or a different version of Windows, or if you have a MacBook, it might go to a different folder. So it may
Joe,
be slightly.
Sorry to interrupt. Can you go toss that link? I realize it's not on our new slides.
Yeah. Okay.
Thanks.
Problem. Sorry. Okay. So, oh, that went to you. There we go. Okay. So just to step back and give everyone a chance, once you navigate to that link that I just put in the chat, you're going to go over to where it says code and select the drop down, and then go to where it says download zip, select that, and then again it will go to your downloads folder, which may be slightly different depending on what kind of Windows or Mac you have. And the decompression step is also maybe slightly different. In my case, I'm just going to select on the file and then go up where it says compress folder tools, and then we'll just do extract all. Make sure when we're extracting this that you erase this extra directory label there. We don't need it. And then we're just going to hit extract. Once you do that, you should see something that says exactly the same name as the zip file. And within that, you should see your 3 files. The next thing we're going to want to do is upload this folder to our Google Drive. So we're going to select on Colab Notebooks, the file that the folder that we set up, and we're going to select new. In this case, we're going to do folder upload. So again, you select this plus sign up here. This is new folder upload, and then go navigate to your downloads wherever you extracted that folder, and then you're going to upload that entire folder just by selecting it and hitting upload. And in my case, it gave me an extra prompt. However, once that's done, again, your directory should look just like this one. It should say my drive, Colab notebooks, /S session _1-main with 3 files in it. Okay. And so with that part done, the next thing we're going to do is actually upload the data, first download and then upload the data from the Activate data website. And in this case, we're going to use the SIT repository, which is just a more graphical user interface type of download. You can also do this programmatically, but we're going to go ahead and navigate to this one that I'm putting in the chat now. So you want to just open that up and navigate, copy that in there. And once you get there, it should look just like this. Right now, we're interested in Activate 2020 data. However, you can also look at the other Activate deployments. If you want to look at data from those, it's an analogous process. And so
maybe, Joe, if you don't mind, maybe just a quick pause. I mean, we can't go through every question, but are there any quick burning questions from anyone at this point? Or can anyone confirm they're still with us who's trying to do these?
I'm trying to download the add-on that you said that you need. Was it
Okay.
what was it again?
So in order to download that, you'll just go over to this from your Google Drive. You'll go over to this plus sign, and then it's Colab with one L, so C-O-L-A. And then you'll see it says Collaboratory, and it should just look like that one.
Yeah, hopefully that works for you.
Thank you.
You're welcome. I've seen that a couple of people are still with us, and Robert, the links will be in the archive for sure. We'll provide the slides and all that information. And Joe, we could probably put the links in the captions of these slides if they don't show up. But okay. I think we're good. I think we're good to march forward. Looks like people are with us, okay, more or less.
So we can see a handful of different platforms here. In this case, the HU-25 is the Falcon, the low flyer, and the UC-12 is the high flyer. However, I'd also like to direct our attention to Merge. Merge is actually a merge of all of the Falcon instruments. So as we showed earlier, there are quite a few instruments that are in the Falcon, and our team, data handling team, has gone through the painstaking effort of lining them all up to a single timestamp, so that everything from all of those instruments can be compared apples to apples. And so we're going to use that one just so that in case anyone wants to look at data other than what we look at here, it's just as easy as changing a few names in the Jupyter notebook to select those specific. So this is kind of a more generic thing. You don't actually need all the data from this merge file just for this one, but I just wanted to mention that and demonstrate its utility. So in order, the data that we're interested in today is from August 28th, 2020. So we're going to select that merge, go down to where we have a 60-second merge, which is just the resolution. It goes one data point for every 60 seconds, just so we don't have so much data. And then we want to select the one that's August 28th. Once you select that file, and you can select anywhere here, you should see where it says review selected files 1. It should show a file size about identical to that. And that's all of our in situ measurements that we need. And then the next thing we need is the leg index file. And this is just so that we can ID which leg the Falcon was flying when we're plotting the data. So that was provided to us by Andrea Corral, and we want to go to that. So we want to go to HU-25, and we want to scroll down to where it says August 28th again, and select that. And now once that's selected, you should see 2 files at the bottom, or review selected files 2 at the bottom. Finally, we want to get the remote sensing data. We have 2 instruments that we're focused on primarily, and those are the HSRL-2, which is the high spectral resolution LiDAR. This is an active remote sensor that actively sends a beam down and receives it based on the difference between the sent and received signal. The HSRL-2 makes a lot of different measurements, including aerosol optical thickness and aerosol extinction, which are both aerosol optical thickness is a 2D measurement of the amount of aerosol in a column of air, and the extinction is just a way of quantifying the amount of aerosol at a given altitude within that column. So the latter is altitude resolved, and the former is just the 2D measurement. So we want to get the HSRL-2 data that's altitude resolved. In order to do that, we want to go down to where it says HSRL-2 UC-12. Make sure it will be an 85 file type, and so we want to select on that one. And you can see once you select that one, the size of your selected files is going to go up a lot. There's a lot of data in that file particularly, so that's going to take the longest to download and upload. And so the last thing that we're going to want to look at is the research scanning polarimeter, which provides us with a series of 2D aerosol properties. And in this case, we want to look at aerosols. So there's
sorry to interrupt. There's a question from Megan in the chat. Are we selecting one of the people's names? If you want to.
Yes. So in order to get the drop down, you just want to select their names. In this case, it's Chris Hostetler for the HSRL2. He's the principal investigator for that instrument. I should have mentioned that earlier. I apologize. So yeah, so you want to select his name and then scroll down to where you find the correct file type or file name, which is the HSRL2 UC12 2020-08-28, and then select that file. And then again, for the RSP, we want to select on Brian Cairns and navigate to where it has the aerosol properties from the RSP, which are noted by AER. And we will scroll down to where it says RSP-AER underscore UC12 and then 2020-08-28. And yeah, just to reiterate too, with the leg index file, it's Andrea Corral, and for the merge file, it's just this one that says merge space 60 underscore second. And then once you have those 4 files selected, we're ready to go. And we just want to click on where it says review selected files at the bottom, make sure you have the correct file selected, and then hit download. Then you're going to sign in if you haven't already. And once you've signed in, it'll take you to a screen where it says loading on the left, which will promptly, once that's done loading, it'll say download, and then we can start downloading the files. This downloading should take about 2 to 3 minutes, depending on the speed of your internet. And once those are done downloading, we're going to upload them to our Google Drive. And so in just a minute, we'll be able to take questions. I just want to make sure everyone gets the files downloaded correctly. But then it'll take 5
Joe,
minutes.
there's a question. I'll just read it to you. What do we do after selecting all 4 files?
Okay. So it's not going to impact me, and also I'm just going to go ahead and. Okay. So once you're done selecting all 4 files, you'll see here, and I just selected one just to show you, but then just scroll down to the bottom of the screen where it says review selected files, and then select that. And then you'll review the 4 files, and then you'll hit download. And then it'll prepare them, and I'm not going to download that, but once that download button pops up, then you select that. And once you've selected that, you should get a zip file on in your downloads folder that looks like this one. That says soot_activate with today's date, and then a bunch of numbers and letters.
Yeah.
So then once those are done downloading, you're going to want to extract that. We don't have to worry about the directory in this case because we're just going to upload the files. You should see a folder that pops up that looks like that, and 4 files in that. Again, you can see the size of the HSRL data is quite large, but it doesn't take too long to upload even still. In order to upload those 4 files, we want to navigate from our My Drive to our Jada session, and then you'll see the 3 files that we uploaded a moment ago. In this case, instead of going to folder upload, we want to do file upload. And so then we want to navigate to where our 4 data files are, and we want to select all 4 of them, and then navigate to where it says open. And once those are uploading, you'll see them at the right-hand part of your screen. It'll take about 5 to 10 minutes for the HSRL2 data to upload. And once that's done uploading, we'll be ready to go for the next one. So now we can take any questions while those are uploading, if I haven't answered them already. I think you might be muted, Armin.
Yeah, thanks, Joe. Someone had mentioned that they see transcript. I'm trying to diagnose what that problem is. But otherwise, anybody else have any questions about anything? On the side, I'm trying to chat about particulates and things like that, more sciencey stuff. Oh, okay. So Joe, maybe you can read what Robert just said.
if you see, yeah, I think I saw that. Did that go away now for everyone? I might have,
Oh,
if I see,
maybe that's a question
I
for
saw that
John.
button. Don't think I needed it, but
So the auto captions have been turned on, and that's the note that is showing at the top of the screen. You can clear that if you want. If you do not want to see the auto captions, at the bottom of the screen there is a button for live transcript. If you click the little arrow there, there's an option to hide subtitle, and that will make it so that you do not see them. If you're not seeing them and you want to, you should click on show subtitle, and that will show the subcaptions.
Yeah, thanks for that. So hopefully that answers the question, Robert. This is a really interesting question from Ramesh about something I had wrote earlier about the sources of particulates over the Northwest Atlantic. So one of the sources might be strange to you, it comes all the way from Asia, and that could be big dust plumes. So the main season where Asian dust is really on the move to come east to impact the United States and even the Atlantic Ocean is March through May. And that's typically the dust season here that we have in the Southwest in our Sonoran Desert. So it's not every day necessarily that the Asian dust is over the Northwest Atlantic in that season, but there can be some episodic plumes that are very strong. So they travel over the Pacific Ocean at high altitudes, but over time, these plumes subside. So it can impact parts of the West Coast of the US, other parts of the US, and can reach as far as the Northwest Atlantic. It's pretty interesting. So with the LiDAR instrument, and we're about to get to the visualization of the data, Joe's going to show you how the LiDAR can give very beautiful vertical profiles of aerosol, and you can see where strong layers are. So often with the LiDAR, we can detect big dust plumes. And using models, then we could see, did the dust plume come from Asia maybe, or maybe the Southeast US, the Southwest US, or maybe even Northern Africa. Yeah, that's a great question. Yeah, so one of the great things about flying in different seasons in Activate is, again, in different seasons, there will be different types of aerosol sources, and the meteorology is very different. So in the winter time when we fly, the winds predominantly come off the East Coast. So you have a lot of the so-called urban outflow from big cities on the East Coast. But in the summertime when we fly, winds are sort of coming from a different direction. They sort of come up along the East Coast, coming up the Atlantic Ocean. So there's different sources. There could be, that's how you can get more of the Saharan dust that comes up to our flight domain, a lot more of the Southeast US pollution sources. And in different seasons, there's different weather and meteorology, and that affects what types of clouds there are. So that's a beautiful thing. We want to fly in different seasons to study different types of clouds, because if we want these climate models to improve, we have to really get them to simulate different types of clouds better. Like there's very thin clouds called stratiform clouds, and then you have thicker cumulus clouds. You can have what are called warm clouds that have liquid drops, and then mixed phase clouds, which have ice. So we fly in all of those, which is, it's really good. We really thrive off these diverse conditions. So these, yeah, go ahead, Joe.
Oh, I was just going to mention, so once your files are done downloading, it should look just like this. Mine are just about to finish, and you'll see the same directory at the top. Make sure that's important because the Jupyter Notebook relies on that Google Drive directory to be the same.
Yeah.
Go ahead. Sorry.
And I can know, you know, these, I know at the beginning, these first few minutes, there's a lot of tedious work to, you know, download these files, but the visualization is really the exciting moment. And these activities are really nice because we've built them for you, and you can use them for courses that you teach. And we're happy to interact with you offline afterwards if you ever run into a problem. But what we're doing for a case flight, you can really apply to almost any of the other flights we have. And if you ever are looking for like a very exciting type of flight with maybe a big dust plume or a wildfire plume, you can email us anytime and we could just point you to a specific flight. You could do the same activities, but just change the flight you download.
Yep. Yeah. And if there's any other like data you're interested in, for example, if you're looking more for cloud data or other aerosol properties that are contained in the measurements, it's as simple as you're changing the names of the keys that you're putting in. And so,
Joe, can you see what Megan just asked? She asked, can you put your file list back on the screen so that she could follow? And Juliet, excellent question about a volcano erupting. So in our data set, we've not had a perturbation from a volcanic eruption, but if one did erupt, you know, some really extreme cases like Mount Pinatubo in 1991 in the Philippines, the aerosol would, you know, go up towards the upper troposphere stratosphere and can just hang around there for a very long time. And those particulates can reflect sunlight and lead to global cooling. So when Mount Pinatubo erupted some 30 years ago, the global surface temperature had dropped to, you know, 1 to 2 degrees Celsius for a period of a year to 2 years, just because of the reflective properties of those particles at high altitudes. If we had a volcanic eruption that influenced our study region, it didn't happen, but if it did, the LiDAR would probably be the easiest one to pick it up because these plumes are at high altitude. And we could probably detect, you know, what layer, what altitude the layer is at.
Yeah. Okay. Thank you. Yeah, I appreciate that. And so we're pretty much ready. I think if anyone can voice in the chat that everything is downloaded, just one helpful soul would be great. And we can just go ahead and finish up the more interesting activities. Okay. Looks like Rory's on board with us. So I'm going to go ahead and continue on. This is really the easy part. Everything else has been hard and arduous to get to this point. From our Google Drive directory, we're going to go to the file that says format and plot underscore data. This is a Jupyter notebook, and once you double click that, you should see a quick loading screen, and then once that's loaded, you'll be in the Colab environment, reading in the data or the information that's contained in the Jupyter notebook. Just to give us a quick primer on how the rest of this is going to go, all we need to do for each step is we need to go to the correct step and then hit the right facing arrow to run that cell. And once that cell's run, there will be generally an output at the bottom, and it'll have a little green check mark next to that each cell that has been run. Just like this, you can see some outputs from this fictional dictionary that we made, and then the check mark. It'll also generally say at the bottom how long it took to run. The first real step is actually just going to, yes.
Just for time management, just so you know, we have 15 minutes, just so you design or how the flow goes, the remainder. Okay.
Okay, gotcha. Yeah, we should be good. So the first thing we're going to do is mount the Google Drive. This just links our Google Colab environment to our Google Drive that we just spent all that time setting up and putting all the files in. In order to do that, you just check that arrow, and then it'll ask you for which Google account. Just make sure it's the correct one, and then hit allow, and that'll just take a moment to execute. And the next step we're going to do is we're going to install the backends that are needed. In order to do that, we go down to step 2, hit run cell. We'll see a bunch of text pop up at the bottom. And in this text, you'll see some red text that says warning. Don't worry about that. It won't have any impact moving forward. It's just saying that the new packages are installed and any variables were erased, but it doesn't have any impact. So you see that warning sign there. Following that, we're going to import those backends. And in order to do that, we'll just, again, go to step 3, hit the arrow button, and then it's done. That one should be relatively quick. This optional step here is just a way to programmatically download data from the Activate Data repository. In case you're really familiar with Python, this can be utilized for that, to let you download a large portion of the data or as much of the data as you want, and be able to do more kind of rigorous analysis with that. But it's not required for this webinar. The next step we're going to actually run is just going to define our procedure for downloading iCart files. This is just something that's going to be called later on so that we can take the data that's in .ict or iCart format and convert it into a Python dictionary for ease for us to actually visualize. So the next thing we're going to want to do is step 5, and that's just reading in the iCart data from the leg index file and the merged data file that we selected. Once you've selected that, run for step 5, you'll see all the different parameters that are available within within that merged file. Anything from gas to aerosol properties to some cloud properties as well, chemistry, size distributions. So anything you might be interested in generally is available in that merged file, and you can change the names going forward if you want to change and visualize different properties. The next thing we're going to want to do is pull in that leg CSV file. So that's step 6. Just hit run there. Following step 6, we are going to generate our time series and our flight track. At the output of step 6, you'll see one figure that's the altitude versus time of the Falcon, and it's labeled by each of the leg types. And then again, the next file will be a latitude longitude plot just showing the flight track of the Falcon that flew again on August 28th. And so just going back to our presentation here, the 2 files that were output, oh, and I'm sorry, I should step back 1 second. Those are actually saved on your Google Drive. So every time you run that, you'll have your output saved automatically so that you can utilize it in your own classes or papers if you go that far with them. And so just to make some notes about these 2 plots, we're plotting here the surface area concentration of aerosol particles, which is as in the same vein as extinction. It's just a measurement of the amount of particles that are there. It's sensitive to both size and count, so just the raw number as well as the size of the particles influence the surface area concentration. It's just a good measure of a good comparison to remote sensing measurements, which are actually more sensitive to surface area than they are just number alone. And just to note, there's a higher concentration generally within the boundary layer, and going lower as you, and that concentration generally goes lower as you go up, but there can also be aerosol layers that are aloft within that aerosol column, and sometimes you might have higher concentrations aloft, which is generally associated with smoke or dust.
I just want to add something too, Joe. So the flight map, you'll see that the flight originated from, it's specifically Hampton, Virginia. That's where NASA Langley Research Center is. And this flight was very special. You'll see a little text box on the top right, because we coordinated the flight such that the 2 planes would be directly under a spaceborne LiDAR. So there's a Calypso satellite platform that flew overhead, and the timing of these flights when we coordinate with satellites is very tricky, and we got it right on this particular flight. So we want to fly right under Calypso because there's a LiDAR in space, a LiDAR on the King Air, and we can compare and kind of validate the retrievals and test them against the in situ measurements from the Falcon. So it's really a beautiful thing. We have 3 major platforms that could be intercompared with one another. So during our 162 joint flights, we did quite a few of these coordinations with satellites in space. But that's all I wanted to add.
And just to visualize that a little bit, you can see this pictogram to the right, which is a illustration of what he was talking about there, how during this flight Calypso was going over top. We had the King Air in the middle and the Falcon at the bottom sampling directly. In this case, don't worry too much about what backscatter is. It's just another measurement of how much aerosol is present in the atmosphere.
Yeah, so you can really see nicely here the LiDAR. We call these curtains. So on the bottom right, it's almost like artwork, but the color coding in the vertical bar is the amount of aerosol backscatter. It's kind of a proxy for the amount of aerosol. So you can see patches of red here and there. So we have a marker that's indicating there are smoke layers on this flight. And so we backtracked where the smoke came from. It was actually wildfires over western parts of North America. So the Falcon cannot get vertically resolved data in a column because it's always moving forward. And the way we remedy that, to answer a question on the slide, is with the LiDAR. The LiDAR, at every moment it's flying, it gets a nice vertical cross section of the aerosol story. It's a very powerful instrument. So that's all, Joe. You can keep going.
And so the next part is actually going to be creating a very similar vertical profile as what you just showed. And again, this will be very easy. All we need to do is go back to our Google Colab environment here, and we're going to read in the data from the HSRL2 and the research scanning polarimeter. And so in order to do that, we'll just hit that run button again on step 8. And at the bottom of that, you should see all the different parameters that are available in those files. And if you're ever interested in anything other than, in this case, we're going to plot extinction, but let's say you wanted to plot backscattering for any particular reason, you would just go and look for the correct name and substitute that in below. And the next step is actually going to be taking the data from those 2 files that we created, or that we put into Python dictionaries, and we're going to make 2 plots. We're going to make one that's going to be the vertically resolved extinction curtain, and the second one is going to be the aerosol optical thickness as derived from both the RST and the HSRL2. And the first one, the curtain, is very useful for getting, you know, information about whether or not there's smoke layers, or just general vertically resolved information. And the second one is useful because we can show the power of having 2 instruments that derive aerosol optical thickness from completely different ways. RSP being a passive polarimeter that just receives the sunlight reflected off the Earth's surface, and the HSRL being the active measurement of using a laser or a light that's being actively pointed at the ground and received. So again, you see 2 plots that output extinction coefficient. This first one is altitude and time, with it being colored by extinction coefficient, and then the second one being aerosol optical thickness versus time. So just going back here, and again, just to note, both of those files were saved just like the previous 2 figures, and that concludes the activity. And that's as easy as it is. And with just spending a little bit of time with these, even for someone that's never used Python before, all the code is annotated and should be easy to understand, so that in case you want to change certain parameters and instead plot surface area, or I'm sorry, backscattering coefficient on these curtains or any of the other parameters, you can do that. And I should also note that this is at a specific wavelength, so these terms are wavelength dependent. In this case, we're looking at the visible wavelength of 532 nanometers.
And Joe, let me add, sorry to interrupt, the question you see on the slide here, do the trends here agree with the Falcon data from the last activity? As you remember, the Falcon, we were seeing higher surface area concentrations at the lowest altitudes in the so-called boundary layer, you know, the bottom 1-2 kilometers. You're seeing that here again too. It's most evident at about 1830 to 1900 UTC time. You can see that there's more green color at the lowest altitude. So a question to you all, you can say it out loud or chat it. What is the main source of aerosol, do you think, right above the ocean that's leading to this enhanced extinction coefficient? Because it's higher than when you get up higher, like at 5, 6, 7, 8 kilometers. You're seeing the most extinction right near the ocean surface. What could that be? Yeah, and thanks. So in the interest of time, I was about to say it, but Rory got it. So sea salt, yeah, over the ocean, sea salt is the major aerosol type being emitted, and sea salt tends to be larger than most aerosol types. So it's responsible for a lot of extinction. But yeah, that's a key point of the combined activities. Put that puzzle together.
And as our final slide, we just have aerosol optical thickness versus time, just showing the good agreement between the RSP and the HSRL2, with some deviations being associated with potentially high-level clouds or uncertainties within the RSP measurement. And so we just want to acknowledge the Activate instrument teams, the pilots, and the data management and archival team, which made this all possible. And if you are interested in doing any kind of collaboration in any form, you can reach out to Armin, and we do have some other information at that activatelarc.nasa.gov. And this is our site for publications. So all the articles that are published around Activate data can be shown here, and can definitely give people ideas for subsequent articles as well. Any questions?
I can answer one question in the chat about how high do sea salt aerosol often reach, 1 kilometer or higher. They're typically confined to the so-called boundary layer. So yeah, within the first kilometer. The main way particles are removed from the atmosphere is through clouds and their precipitation. We call this wet scavenging. When a cloud rains, when it's raining, it removes the particles that made the droplets, which are often based on sea salt particles. So, these boundary layer clouds hover around, around a kilometer over the ocean, over the Northwest Atlantic. So that's the main route of removing the particles. Otherwise, the particles have a better chance of going up higher. It's not uncommon for sea salt particles to go up higher, but typically it's within the first kilometer. So, yeah.
And that boundary layer can be different depending on where you're at. If you're off the coast of California, it can be higher. It depends on the meteorology. And so, yeah, there are definitely a lot of studies that investigate where that boundary layer lies and how high the aerosol goes in those cases. Yeah, that's a very interesting question.
I know we're at the end of our hour. I just want to...
you're muted again, Armin.
Yeah. Hopefully you can hear me now.
Yes.
Yeah. Just want to encourage anyone, I know we're at the end of our hour, to reach out to myself. I'm happy to help answer more questions along with Joe, and to maybe work with you in terms, if you think this could be of interest to coursework activities. We'd love to help you. And if you're interested in the actual science, that's great too. We'd be happy to talk more to you about collaboration and ideas that you could run off with. So. Yeah,
great. We are coming down to the end of the hour, so I just wanted to thank Armin and Joe for that webinar, and thank everybody for participating in today's webinar. Before we wrap, I did want to let you know about the next webinar. It's coming from the Compass Project and is entitled Discoverability, DEI, and Accessibility. And you can find out more about that at the link that I'm dropping into the chat right now. Also, please take a moment to provide some feedback about today's webinar. These feedback surveys are really important to us because it helps us continue to provide the kinds of webinars and professional development experiences that are meaningful to NAGT membership. So please take a minute. You'll also be getting an email with that evaluation link in it. But if you can take a couple minutes and give us some feedback, that would be awesome. Otherwise, we will go ahead and wrap it up. If Armin and Joe are available to stay on for a couple more questions, that's great. But I'm going to go ahead and end the webinar recording so we can carry on with our day. Hope you all have a great afternoon.
Thank you.